Thank you so much, Dr. Dipti, for giving me this opportunity. Professor O.D. Mackenday obtained his PhD in applied mathematics from University of Bristol, United Kingdom in the year 1996. His research covers a broad range of topics, including fluid mechanics, nanofluid dynamics, heat and mass transfer, hydromagnetic stability, dynamical system, biomedical. He has taught, supervised, and mentored several students at undergraduate, postgraduate, and postdoctoral level. He guided 33 PhD, 72 MSc, and 200 BSc students in the field of applied mathematics and computing, presently working as a distinguished professor of applied and computational mathematics at the Faculty of Military Science, Stellenbosch University, South Africa. He is also visiting professor of several reputed universities like Adama Science and Technology University in Ethiopia, African University of Science and Technology in Nigeria, Nelson Mandela African Institute of Science and Technology in Tanzania, Pan African University Institute of Basic Science, Engineering, Technology and Innovation in Kenya, and BIT in India. Professor McInnes served as a senior professor and director of postgraduate studies and the founding director of Institute of Advanced Research in Mathematical Modeling and Computation at the Cape Peninsula University of Technology, South Africa during the year 2008 to 13, and also worked as a professor and head of the department at the University of Limpopo, South Africa in the year 1998 to 2008. Professor McInnes served with many prominent positions like Secretary General of the African Mathematical Union during the year 2009 to 17, the Vice President and General Secretary of the Southern African Mathematical Science Association during 2002 to 6, and etc. Professor McInnes is a member of editorial board committee of several international national reputed journals such as Journal of Applied Mathematics, Africa Mathematica, Journal of Nanofruit, Journal of the Nigerian Mathematical Society, the Open Chemical Engineering Journal, PLOS One, etc. Professor McKinley edited two research books published in Diffusion Foundation and Defect and Diffusion Forum. Recently, in the year 2020, he edited another research textbook titled Engineering Fluid Flow and Heat Transfer Analysis, published in Diffusion Foundation, and Computational Analysis of Heat Transfer in Solid, in Fluid and Solids, published in Defect and Diffusion Forum. He is the lead guest editor of two special issues and also serving as a reviewer of many reputed journals. In addition, Professor McIntyre is the author of Applied Mathematics textbook and monograph and published over 500 high-impact research papers in several reputed international journals. Professor McIntyre is the recipient of 2014 Nigerian National Honor Award for his outstanding contribution to mathematical science and technology in Africa by the President of Nigeria. He is the winner of many prestigious awards like African Union Kwame Nkrumah Continental Scientific Award, Best Senior Research Scientist, Scientist Award at the University of Limpopo, Best Senior Research Scientist Award at the Cape Peninsula University of Technology. Professor McKinley is the winner of Research Scientist Award at the Faculty of Military Science, Stellenbosch University from 2016 to 19, and the Chancellor Award for Outstanding Research Excellence in Stellenbosch University in the year 2019. Professor McKinley received a prestigious Fellow of the African Academy of Science for outstanding contribution to science, innovation, and technology in Africa in the year 2012. He was also awarded a Fellow of the International Academy of Physical Science for his outstanding contribution to the field of mathematical science in the year 2018. Professor McKinley organized several conference, workshops, and symposia within and outside the African continent and delivered keynote research papers at the several national and international conferences and workshops worldwide. He has an extensive record of research and academic collaboration with several faculties and universities with many countries. Thank you, Professor McKinley, and warm welcome to seminar. Thank you.
Thank you, Dr. Rohit Sharma, for that nice introduction. We now request Professor O.D. McIntyre to take over the session.
Yes, thank you very much for that excellent presentation.
Thank you.
I'm very, very grateful for inviting me to share knowledge at this prestigious international. It gives me that for us to share knowledge on the matters. Can you hear me?
Yes,
Hello?
sir. You can proceed.
Okay. Now, so okay, thank you very much. Thank you very much. Okay. So this is an opportunity to share knowledge across the globe on the aspect of research. And I thank the organizer for giving me the opportunity also to be part of this august occasion of a webinar, international webinar in sharing knowledge in the field of mathematics and its applications. I will also need to appreciate God for giving us this opportunity, because in this period of COVID-19, it is extremely difficult worldwide to interact the way we normally do in terms of conferences, seminars, and the colloquium. But we thank God for giving us this opportunity, this platform, to still continue to interact and share knowledge in the field of science, technology, and engineering and mathematics. That is extremely important. And we thank the organizer for taking this initiative. So thank you very much. I'm very grateful for giving us this opportunity. Now, let me proceed by introducing you properly to my talk today. And as you know, in science, nobody knows it all. We all share knowledge and improve on our science and engineering, and we contribute to development of technology that make life better in the universe. So the topic of today shows the application of mathematics to engineering, science and technology in terms of improving the innovative devices that we are using today. The title is Modeling Stagnation Point Flows of Nanofluids and its Engineering Cooling Applications. What do I mean by that? You will see in the presentation. The overview of my presentation is as follows: introduction, application, then you have literature review, fundamental equations, model formulations, numerical approach, numerical results. Then you have a conclusion, and then also references. Now, what is stagnation point flow? Stagnation point flow is a point on the surface of a body submerged in fluid flow where the fluid velocity is zero. You can see from this picture which you have here, you can see this point when the fluid is flowing. This is a body, and the fluid flow and contacting the surface of this body. There is a point here where the velocity of the fluid comes to zero. And when the velocity of the fluid comes to zero, that point where you have such is called stagnation point. So when you want to cool a surface, when you pour fluid on the surface, you get to a point, the velocity remains zero before it starts spreading around the surface. This point is called stagnation point. A stagnation point is experienced in all surfaces that are being cooled, where you are cooling a surface or you are pouring fluid on top of a surface. The fluid will get to a stagnation point before it starts spreading on the surface. So what is the importance of stagnation point? Stagnation point is very important because you experience stagnation point in every engineering cooling surfaces, every surfaces where you pour fluid. For instance, in aircraft, when you have aircraft, you will see that the aircraft is flowing across and there is a wind and fluid and air blowing across, it means the surface, it hits a stagnation point and spread around the surface and creates what we call boundary layer. It creates boundary layer around the surface. That is, whenever you have a stagnation point, there is a boundary layer, which is a thin layer of fluid spreading around the surface. This is a stagnation point here, and you have a thin layer. You can see from this diagram, when you have a fluid pouring on this surface, and when the fluid hits this surface, it reaches a stagnation point and continue to spread and create a boundary layer around this surface. The concept of stagnation point is extremely important because it's experienced on any surface that where you have an external flow over a surface, it hits a stagnation point. So it exists at surface of object in the flow field where the fluid is brought to rest by the object and before it starts spreading. The velocity decreases as the fluid approaches the stagnation point. Like velocity is here, as it approaches stagnation point, velocity decreases or becomes zero, and now it starts spreading around the surface. So that is the meaning of stagnation point. But why do we need it? Why do we need to study it? You will see later. And part of introduction also, we look at what we call the concept of Navier sleep condition. The surface, remember, this surface may be rough condition. Normally, when the surface is rough, when the fluid hits a rough surface, the velocity of the fluid becomes zero. That is, you have velocity of the fluid becomes zero at the surface. That is what we call no slip condition. No slip condition means when the fluid hits a surface, the velocity of the fluid is zero. If the fluid, if the surface is stationary, the fluid stays on the surface, the fluid is not moving. If the surface is moving, the fluid moves with the surface. That's what we call no slip condition. No slip condition means at the solid surface, stationary surface, the velocity is zero. And this happens when the surface is very rough. But when a surface is lubricated, there is tendency that the fluid slip on the surface. That slip condition, that slip can be linear slip or non-linear slip. Navier in 1823, he proposed what we call a kind of linear slip, that the rate of slip of the fluid of the fluid on the surface is proportional to the shear rate at the surface. It's proportional to shear rate, and it's a linear proportional to the shear rate. This is what we call Navier slip. Although the shear rate may be non-linear, for instance, depending on the rate of slip on the surface, but we call this one Navier slip, which is a linear relationship between the shear rate and the slip and the slip length, which is beta, that is slip parameter. So we call this one Navier slip. If beta, you can see here now, if you divide mu, this beta is called slip parameter. Mu is the dynamic viscosity. Now, if you divide mu by beta, you can see if beta tends to infinity, this one will be zero. That means no slip condition. When beta is zero, you have a perfect slip. That means the surface is highly lubricated. A highly lubricated surface, a highly polished surface, have beta to be zero. Beta is zero when the surface is highly lubricated. That means a fluid getting to that surface will slip. That's lubricated surface, highly lubricated surface. But if beta tends to infinity, you have no slip condition. So this condition you have here is called Navier slip condition. It combines. You can use this condition to look at different types of surface, whether the surface is partially lubricated or totally lubricated, or is non-lubricated surface where you have no slip condition. So we are going to make use of this to look at stagnation flow, point flow, where you have different types of surfaces. Because in engineering, you can engineering surfaces, solid surface, you can have different types of surfaces. So this is part of what we are going to use in the model. Also, I told you earlier that it's what we call bandy layer. What is bad? When you have a stagnation flow, the fluid hits the surface and spread on top of the surface. And when the fluid is spread, is moving on top of the surface, there is what we call bandy layer. A bandy layer is a thin region between the surface and the fluid, where the effect of the fluid velocity, temperature, and concentration is felt. That is where there is variation in the fluid velocity, temperature, and concentration. That's called bandy layer. So you can see here, this is a kind of a bigger view to see when the fluid hits the surface. If this surface is if the fluid is coming like this, it hits this surface and it's flowing across this surface. Here at the point of entrance here, the velocity will be 0 because this point, this is the velocity U, capital U, hitting this is flowing across this surface. At this point, hitting the surface, there will be stagnation point before it starts flowing on top of it. When it's flowing on top of this surface, you will see that the fluid close to the surface will be brought to 0. As we are moving away from the surface, the velocity of fluid will be increasing. Although the velocity is coming to big U, that will be increasing until you get to final big U. So you can see between this point of 0 velocity, it's increasing until you get, there is a variation in velocity until you get to this maximum big U. This big U is called free stream. This part is not affected by the by the surface. But as you are moving away from the surface, the velocity is increasing until you get to the free stream velocity. But as moving close to the surface, velocity is increasing until it reaches the point on the surface. And if there is no slip, velocity is 0 due to no slip. So therefore, this issue, this variation in velocity, this region of variation in fluid velocity, and even temperature or concentration is called bandy layer region. This variation affects the surface because it creates friction on the surface. The fluid is tend to move across, the viscosity of the fluid is felt close to the surface. It creates friction. It creates what we call shear stress. So within the bandy layer, we want to see the effect. What is the size of this bandy layer, where the effect of the fluid velocity can be experienced? And that's also, we want to know the size, the skin friction, the temperature, and concentration. This is very important where you have stagnation point flow. It's also important where you are cooling a surface. This concept was pronounced or was innovated by Prandtl. That's why I call it Prandtl bandy layer. And one of his students is Blasius, who work on this type of a flat surface where you have a kind of bandy layer or flat surface. And he uses a similarity variables to reduce the Navier-Stokes equation to a kind of, which is a kind of a partial differential equation. You use this similarity variable to reduce it to ordinary differential equations and able to obtain the thickness of the bandy layer and the skin friction of bandy layer. That's Blasius in 1908. Those are the earlier work done. But today, many work has been done on bandy layer to extend, to really prove the concept of, the applications. And some of the applications can be found in airfoils, in aircraft, developing of aircraft wing and the surface, even in the automobile, the concept of bandy layer, in ship, turbine blades, industrial cooling of all surfaces, and so on and so forth. But today, we are going to look at the application of bandy layer with respect to industrial cooling of hot surfaces. So those are part of introduction. Let me now go to introducing nanofluid also. Remember, I've introduced to you the concept of stagnation point flow. I've also introduced to you the concept of a bandy layer, because stagnation point flow bring about the concept of bandy layer as well. Now, we want to talk of nanofluid. We are talking of fluid. Which kind of fluid are we going to look at today? So I'm going to look at what we call nanofluid. What is a nanofluid? Nanofluid is a mixture of base fluid, which is called liquid, and nanoparticle, which means a particle of size 10 raised to the power minus 9. Of size 10 raised to the power minus 9. That is, the particle has been fabricated just like a powder, which you see here. This is aluminium. This is water. Base fluid can be water, can be oil, can be ethnic glycol, can be polymer solution, biofluid, and so on. And nanoparticles can be metallic or non-metallic materials. Like I have aluminium, copper, silver, gold, ferrous, iron, and so on. Oxide, ceramic, metallic carbide, nitride, non-metallic material, and so on and so forth. Why do we need nanofluid? Because you know that the base fluid, like water, like oil, and so on, their thermal conductivity is very, very low. That is, the rate at which they can conduct heat, the rate at which they allow heat to pass through, they can transfer heat. Their heat transfer capacity is very low. Their thermal conductivity is very low. Thermal means heat. The rate at which they can conduct it is very low. Therefore, when you talk of solid material, metallic material, like iron, like silver, like copper, and so on, those materials have high thermal conductivity. They can conduct heat. Heat can pass through them very fast. But both of them have advantages and disadvantages. Copper, metallic and non-metallic, they are solid. They cannot move. They can't flow. Solid cannot move. They can't flow on the surface, although they can take out the heat. Liquid can flow on the surface, but liquid cannot take out the heat very fast. And the major problem of engineering is thermal management. How do we manage it? When a machine, engineering devices, when they are in operation, they generate heat. And this heat they generated, if it's not taken away quickly, they can lead to thermal runaway and destroy the device. So the major problem in engineering today is thermal management. How do we manage the heat that is being produced by our devices so that the devices can last very long? And to do that, the concept of nanofluid comes in by mixing, by combining the base fluid and the nanoparticles, particles of the solid materials. And it was observed experimentally, taking only 1%, just 1% of nanoparticles, mix it with conventional fluid. The thermal conductivity of conventional fluid will be enhanced, will increase greatly, up to 25%. You can see this one. When you put 0.1%, this is what you have. 1% is what you have. When you can see 0.01%, 1% and 0.1 and 1%. And if you test this, take small this one, the thermal conductivity of this liquid is very, very high compared to where you have here. It has been increased by almost 25% or 30% when the experiment was done. So it can take out heat faster. It can be used as a coolant, better than using this. And that increase, that 10% or 30% increase, it can do more good in making the life of the material to last longer instead of accumulating heat. So those are the concepts of nanofluid, and I've already explained. You can see on this table, engine oil, ethylene glycol, water, aluminum, and so on. You can see their thermal conductivity is very low. When you come to solid material, number 4, aluminum, silicon, copper, and all those. As we are moving from 4 to 9, you can see the thermal conductivity is very high. So if you only use this one as coolant, your result will not be very good. But by taking this and mixing it with very small percentage of this, you get a very good result. That is the reason why we need nanofluid. That's part of the introduction. What are the application of nanofluid? You use nanofluid for nuclear plant cooling. When you have a nuclear plant, it generates a lot of heat. And for efficient operation, effective operation, you have to use nanofluid in cooling some of these nuclear plants to make sure that the operation is efficient and there's no explosion in nuclear plants. The same thing, electronic devices. Nanofluid is used in cooling electronic devices. Automobile. In automobile, the car you are using, you have coolant. The coolant is made up of nanofluid. You put water, you have to mix it with nanofluid in your radiator to make sure that the engine, cooling of engine as you are driving the car, whether it's aircraft and everything, the coolant is used. Coolant is a nanofluid used to make sure that the engine cool properly as it generates heat and it can operate without any problem. The same thing in industry. In industry, where you fabricate materials you fabricate, like metallic materials we fabricated, they are in liquid form. When they are in liquid form, you use nanofluid to make sure that they are in proper shape. After you fabricate them in liquid form, you cool them to nice shape, the shape you want. In when you talk of metal casting, when you are casting metal, nanofluid is using in cooling the metal you have casted in liquid form into a proper shape, in cooling them to form shape. Also, there is medical. You can coat nanoparticle with medicine because nanoparticles, they are susceptible to magnetic field, and nanofluid is susceptible to magnetic field. Therefore, coating nanoparticle and inject it with drugs to kill cancer cell. You inject in the body, subject it to magnetic field, you can see that and target the cancer cell, that the magnetic field will generate what you call jaw eating, and we make sure that the nanoparticle will be attracted to that cancer cell and destroy the cancer cell. So there's medical application, even in military. In military, you have the application of nanofluid. Most of the military materials during operation, they generate a lot of heat. You can see here, there's a lot of heat generated in military operations. Now, nanofluid is used to cool down the military devices so that they can work efficiently. Otherwise, the heat they are generated can lead to destruction of military devices. Like all these gadgets, they are being cooled down during operation using nanofluid to make sure they're efficient, they're sufficient operation, because they generate a lot of heat. So those are some of the applications of nanofluid, which we are now, in terms of the talk of today, many people have worked on these aspects I'm talking about. There are a lot of researchers. The concept of nanofluid experimentally was introduced by Cho. Thereafter, there are many work in 1995. There are many work that has been done in the issue of nanofluid. You can see so many work, even recently, 20s, you can see the work done by Liu on the area of thermal conductivity of nanofluid experimentally. And it was reported that taking only 1% of nanoparticle, mixing it with base fluid, it enhances the thermal conductivity, makes it a better coolant, or it's used for what we call heat exchanger. For heat exchanger, that is to transfer heat. It enhances the heat transfer. So that has been discussed experimentally and theoretically also. This has been done and there are a lot of work I've done myself in this area also, and with some of my students, we have done a lot of work in the aspect. Let's go to the fundamental equations needed for today's work. Remember, this concept can what I'm going to talk about is a very broad research area. But I'm going to focus on one area, and I will tell you how you can extend it to a lot of work. For today's work, the fundamental equation of fluid mechanics, which we use, fluid dynamics, will be this, that is continuity equation. That is, we assume that our nanofluid, the fluid that we are using for stagnation point flow, is incompressible, which means the density of the fluid is constant. The fluid density is constant, or is roughly constant, averagely constant. That is what we mean by saying the fluid is incompressible. Also, the fluid, I'm going to talk the conservation of momentum I'm using for this model will be the Navier-Stokes equation, which already assumes that there is a linear relationship between the constitutive equation is linear between the stress and strain. There's a linear relationship between stress and strain and the incompressibility as well. So this is Navier-Stokes equation, and our body force, which we have there, is magnetic field due to Lorentz force. Lorentz force here have this term J cross B, where J is current density, B is the magnetic field imposed. That means our nanofluid is a conducting nanofluid. It's subjected to electrical conductivity. It has electrical conductivity. Where V here is my velocity vectors. Rho here is the density of nanofluid, where mu NF here is the dynamic viscosity of nanofluid. P is the pressure. Remember, this has assumed that my nanofluid is a Newtonian nanofluid. You can also have non-Newtonian nanofluid. In that case, this term will change. This term, which is the viscous term, this time I'm touching here, will change. If you are dealing with non-Newtonian nanofluid, this time will change. It's because we are going to have non-linear relationship between the stress and strain. You can have third grade fluid, second grade, you can have physical elastic, whatever. Then this time, but in this case, I'm talking of Newtonian nanofluid. Newtonian nanofluid. So this is the energy equation. The energy equation we have here, and this is our thermal conductivity of nanofluid. And this one is a viscous dissipation. And this is what we call the Joule heating, where J squared over sigma. Sigma here is the electrical conductivity of nanofluid. And sigma is, it can be additional heating. If there is any radiation absorption or internal heating, additional internal heating, or there is a absorption of radiation or heat sink, heat source, you can add it. But this heating J squared over over sigma is called the Joule heating due to the magnetic field, due to the presence of magnetic field. And Cp is specific heat at constant pressure. So this is energy equation. Remember, because we have magnetic field as our body force, there is the Maxwell equation we call me. The Maxwell equation, which is the equation of electromagnetism, we call me. And under that, you have your Amps law, Faraday law, and Ohm's law. All these one, we contribute, we will use in the body force here. So this is very, very important. And we assume that the magnetic field imposed is uniform and constant. Therefore, the generation of electric field, we are going to assume is negligible because we are having constant magnetic field. It's not varying. Because when magnetic field varies, according to Faraday law, electric field is produced. So this is a general equation. Now, let's go to the nanoparticles. Nanoparticles, this one that is a small in the nano, it's also nanoparticles and the base fluid properties. Here I'm going to use pure water as my base fluid. These are the thermophysical properties of pure water. This one you can obtain it from engineering textbook. Is there in every, is experimentally obtained. You can get it from journals, from literatures and engineering textbook. I'm using copper and aluminium as my, you can see this one as my nanoparticles. These are the thermophysical properties. You can see the electrical conductivity of water is very, very small, and that of copper is very high, and that of aluminium is also very, very high. So, but we have nanofluid is a mixture. So these are their thermophysical relations for density. Wi-Fi here is what we call the volume fraction, the amount of nanoparticles you are introducing into the nanofluid. If phi is 0, there's no nanoparticle. Rho F is your density of of base fluid. Rho S is that of nanoparticles. Similar to here, the specific heat for base fluid for nanoparticles, and so on. This one is electrical conductivity. Sigma F is that of base fluid, and sigma S is that of nanoparticles. All the properties are here, which we are going to use. Remember, if phi is 0, you only have base fluid. If phi can be 0.1, 0.2. When phi is 0.1, maximum 10%. Phi 0.1 means your nanofluid is having only 10%. You can have 0.01, which is 1%, and see effect as you are increasing. But you should not use more than 0.1, which is 10% of your material is filled of nanoparticles. This is the electrical conductivity, the thermal conductivity. And we assume that our nanoparticle is a cylindrical in shape. That's why we have this. If it's not cylindrical in shape, it will not be of this. Anyway, those studies. Now, you can see this model problem now. Let's go to the model. You can see the model problem. We assume this is a material here. This material can shrink, it can stress. Under here, you can see heat is generated here. Because this material is heated, you can see where this material, heat is here, is heated up. You can see the heat in here below. This material has what we call it is a material that can transfer in the surface. This is the surface. This heat can be a chemical reaction taking place that generates heat. It can be a chemical reaction. It can be nuclear plant reaction. It can be coal, by coal. It can be, so heat is generated under, and this heat is heating up the surface. If this heat is not taken out of this material, this surface can break. There can be explosion. Therefore, you need a coolant, a nanofluid you pour on this surface to take out the heat out of this surface. Meanwhile, this reaction is necessary. This heat generation here is necessary because this reaction is what is making your material, your devices to work. It makes your devices to work. As this reaction takes, your devices is working well. But generating heat, you must cool it. This, and the surface here can stress, can shrink, or can be stationary. This is for stressing surface. And this one is for shrinking surface. You can see surface is shrinking. And you are putting nanofluid. And this nanofluid, where you are putting nanofluid here to cool the surface, it is regulated by magnetic field so that the cooling can be very, very efficient. Because magnetic field, it reduces the speed, it decreases the speed of the flow rate of the nanofluid on top of the surface to make sure that nanofluid take out the maximum heat on the surface. Because as you are pouring it, the magnetic field slow down the flow rate. Remember, the surface can shrink, can stress like this, or it can shrink, or it can be stationary. So we are going to look at the three, either stressing, shrinking, or stationary. So when you have that, the research question is that, what do we do? What do we do? That's the research question. What can we, under this condition, we want this surface to cool properly. We don't want this surface to be damaged by nanofluid. We don't want it to be too much accumulated so that this device will not work well. You don't want your nuclear reactor to explode. You don't want your electronic devices to melt down. So therefore, we must take out the heat by putting this external flow to be cooling as heat is generated within. So what we do, to do that, we have this model. The model equation we obtain from the Navier-Stokes equations is this. You have this one. That's the model similarity equation. And this is obtained from the momentum equations which I've shown you, and from the continuity equation. You obtain where F here, derivative of F represent the velocity. Here we have used similarity transformation. You turn the PD to OD, you get this one. Where M here represents your magnetic field parameter, which is the square of the Hartmann number. And for the energy equation, theta represents the temperature. This is what we obtain. Where E here is the Eckert number, Prandtl number. F represents the stream function, which also the derivative represents the velocity profile. PR is the Prandtl number. Where all these A1, A2, B1, and so on, they are from the thermophysical properties of the nanofluid, which I've shown you before. And here, this one is taking, it is going, this is a coolant. It is going here. There is a coolant taking the heat away and cooling the upper surface. So here, there is a convective heat transfer below. So we have this Bout number, BI is Bout number. And it's based on Newton's law of cooling. The rate at which heat is being transferred through this surface, under surface to the outer surface. That is this. Increase in BI means increase in rate of heat transfer between the below and above, and here getting to the nanofluid. And that is for temperature. And here is the velocity. Velocity condition here means lambda here it talks about the stressing. If lambda is positive, you have having stress. The surface is stressing. If lambda is 0, the surface is stationary, it's not stressing. If lambda is negative, the surface is shrinking. As here, we assume the surface is slippery. The surface of the upper surface here, it can slip. We pose a kind of what we call Navier slip. That's a slippery condition. The surface can slip. That means when the surface, there is tendency for the surface to slip. There is some amount of slipperiness of the surface. The surface is a bit lubricated. It's not that it's totally lubricated. So you can find some of the fluid can slip a bit on the surface. So the aim of this is to simulate the reality of the upper surface where the fluid is touching to take out the heat. If S is 0, that means there is no slip on the surface, no slip condition. And this one calls for the velocity. The fluid is not that is entering, is hitting the surface, is not coming down. This surface is not permeable. Therefore, you have F here at the surface. This is 0, eta is 0, eta is 10 to infinity, far away at the free stream. So F of 0 means the surface here is not permeable. So those are the things. And this free stream condition, theta infinity means this at far away from the surface, you have the free stream condition. And the velocity at the surface, you have the free stream velocity. Like surface as it's coming, the fluid is coming, the velocity here, we know. But going to the surface, there is boundary layer. So there is a decrease in velocity of the temperature, or temperature, there is a variation in temperature and velocity of the heat the surface. So this is the model equation, which is obtained from that of the basic equation, which I've shown you earlier. We derive them from here. Now, these are the assumptions. These are what we use, which I've already explained. Yes, you can see here. These are the value. This is temperature, dimensionless temperature, Prandtl number, IKL number, Bout number, and so on. And you have this one, the velocity of the surface, which are used. All these are introduced, and these are similarity variable introduced. It's similar to what you call the Blasius similarity variables, by putting this velocity to be of this form. There's a linear stressing of the surface. And the free stream velocity also, we take it as a linear velocity, function of x, free stream velocity. That gave us these from Blasius similarity variables. If you use that, you get the equation I got. This is magnetic field, which is the square of the Hartmann number. So you have this parameter as follows. The screen friction is defined as follows, and the Nusselt number is given as follows. So we are now going to work on this and solve the problem. How do we solve the problem? This problem, remember, when you get this equation, this is a non-linear problem. You can use any mathematical method to solve it. You can use Adomia decomposition method. You can use homotopy analysis method. You can use any approximate method to tackle this problem. Any approximate numerical method or semi-numerical method, any approximate mathematical method, you can use to solve it. You can use finite element method, finite difference method. Any method you can use, but each of the method, take note, all the method you use to solve them, they are all approximate method. They are not exact. They don't give you exact solution. Therefore, they all have the advantages and disadvantages in terms of accuracy of the solution. But you can test the accuracy up to certain level. And that's what we did. In this case, we use shooting method. Shooting method means you transform the boundary value problem. This problem is a boundary value. You can see you have boundary conditions at 0 and at infinity. Infinity here means far away at free stream. It's not actually, you don't mean, it means far away. Infinity can be at eta equals to 10, equals to 11, and so on. You will detect it when you are doing your numerical simulation or whichever method you are using. So what we did here is we changed the boundary value problem to initial value problem. And we get them as initial value here. We now, the unknown initial value in the system, like A1, A2, we obtain them using Newton-Raphson's method. We guess the initial value and using Newton-Raphson to obtain the actual initial value or no initial value, and use Runge-Kutta to solve the resulting initial value to get accurate. The advantage of this Runge-Kutta Feinberg method, Runge-Kutta of order 4, order 6, order higher order Runge-Kutta, the advantage of it is that it makes your work more accurate, because the order of accuracy of Runge-Kutta of order 4 is 4th order. Of order is high. You can use Runge-Kutta Feinberg method. All these things are already in softwares. You can use different softwares. MATLAB have inbuilt program for it called BVP. Mathematica, MATLAB, they all have inbuilt program if you know how to use it. Or you can write your own code. You can write your own code in Fortran, in anything to develop and read and solve the problem. This is one way. You can also use finite element and so on. Like I said, you can use the homotopy analysis method and solve it as well. They are all approximate method. Anyway, when you do the solution, this is what we got. Numerical result is as follows. So you have the computational impact. You can see here of different nanoparticle on critical shrinking parameter. For shrinking, we realize that for shrinking, there is a dual solution. Dual solution exists for shrinking. And the dual solution we obtain is that there is a solution for here now. You can see for copper water, when you use copper water as your working fluid, and you are is shrinking. Shrinking is when the lambda is negative. There is a critical shrinking parameter. This one refers to, the black one refers to copper water, where the dotted line refers to ferrox water, and you have aluminium water for the red one. You can see that the critical value, if you use copper water as your working fluid, nano fluid, the rate of the shrinking, if you are putting as shrinking, there is dual solution. This upper branch and this lower branch, and there is a critical point, and this is the critical point where lambda is this. So it can shrink up to lambda C, which is minus 2.7 here, minus 1.25, minus 1.257. So which means for copper, the rate of shrinking for copper water will be more. If it's your working fluid, it will shrink more up to this point and stop. If you are using copper water for your cooling, for cooling the system, and the surface can shrink, it will shrink more than using ferrous oxide water or using aluminium water. So the rate of shrinking will be more for copper water. So, and then this, it will shrink up to this point. Here it will be less, here it will be less. So, and this upper solution, we got it from our numerical simulations, that there are dual solutions for shrinking. But for stressing, only single solution, unique solution occur for stress, only one solution. But for shrink, you have dual solution. That is this one solution, the other solution. And that's what we obtain here. So these are the shrinking parameter. That means you have two solutions, which is very, very interesting mathematically. But in terms of engineering, we discovered that the upper solution is the physically realizable solution where you do the stability. Experiment will only show you the upper solution. The lower solution is there because of the non-linearity of the problem. So that is what you have. Let's look at, for shrinking also, the effect of nanoparticles. When phi is 0, there is no nanoparticle. Here I'm using copper water only to test. The same result we apply for when you use aluminium water or when you use ferrous oxide water, but it will be different value, but the trend of the result is the same. When you are using only water as your coolant, you can see the critical value. Critical value you see here, you can see when is 0 is 1.2. I mean, the critical value is minus 1.254. When in 0. When you use 5% of nanoparticles, you can see it's minus 1.26. When you use 10%, when phi is 0.1, 10%, the critical value is minus 1.27, which means that as you are when you know the shrinking rate of your surface that you are cooling will be more when you use nanoparticles. Increase in nanoparticle volume fraction means increase in shrinking rate, which means increase in cooling rate of your surface. The surface cool more. This surface can shrink, but the cooling rate of the surface is more. That's why it's shrinking more. So the more the increased nanoparticle volume fraction in your base fluid and in your coolant, the more shrinking the surface will be, and which means the better the cooling rate of your surface. If the surface that can shrink, it will shrink more and cool better. So that is what is happening here. And you can see, although the dual solution here is the dot one means lower branch, and the dark one means the thick line means upper branch. You can see this is upper branch, upper branch, upper branch. In terms of experiment, upper branch is the one you will find The lower branch are mathematical results. They are unstable. In terms of stability, they are unstable because we did the stability analysis of the lower branch and upper branch. We see that the upper branch is stable because of the eigenvalue we got. So the experimental result will show you the upper branch. Mathematical result show you the dual solution. Dual solution occur due to multiplicity of due to the non-linearity in the model. So that's what you have there. So nanoparticle is very, very good. It enhances the cooling rate of the solid. Take out the heat and make it to shrink better. What are the effects of stressing? I mean, of sleep effect. When the surface is slippery, when the slippery rate of the surface increases, what do we got? We can see here, when you have S to be 0.1, critical value for the shrinking is this, minus 1.08. When it's 0.2, minus 1.13. So as the surface becomes more slippery, the shrinking rate increases. You can see the surface shrinks more if the surface is polished. First, you are cooling. If it's a shrinking surface, and you are cooling it, the surface will shrink better. So, which means lubrication also of the surface can enhance cooling rate. That's what you can see. So, if a surface is a shrinking surface, it shrinks better when the surface is lubricated compared to when surface is coarse. If it's a coarse surface, then the cooling rate will be minimal. The shrinking rate will be minimal than when the surface is slippery. So increase in slippery rate of the surface will increase the shrinking of the surface. And this is the critical, like for here, you see, it's shrink to this point. But when it's 0.2 is this, when it's 0.4, I mean when it's 0.4 is this one. It shrinks further. When it's 0.1 is this, to this point. And these are the secondary solution, which is lower solution branch. Those are dots. The dark one and the, so you can see the effect of all these parameters. This is very, very important mathematically. It shows the effect of the non-linearity of the model. And you only observe this when you have shrinking, when the lambda is negative. And in terms of mathematics, you see that when you get here beyond this critical value, you see that the solution will be imaginary. You only have the solution up to the lambda c. Beyond it, when you go beyond this value, when you go to -2, minus this and that, you are not going to have solution. Your numerical solution will say not a number. It's imaginary. So just take note of that. And you can see the impact of different parameters like that. So, and you let's see the impact of this impact of magnetic field. You can see magnetic field. When magnetic field is open, this one is supposed to be magnetic field M. This one is S. S is 0.1. This is M. I mean, sorry, this one is M here. So you can see the graph here. This for M, you can see when M is 0.1, you see here the critical value is minus 1.274. Minus 1.274. When it's as you are increasing the intensity of magnetic field, the shrinking rate also increases. You can see this one, the dark one, the black one represents when my M is 0.2. While the blue one represents when M is 0.1. So as you are increasing the intensity, the shrinking rate of the surface increases. That is very, very important. It tells you that magnetic field also enhances cooling of the surface. Because magnet reduces the velocity of the nanofluid on the surface, so that now you can take more heat. The more heat that is taken out of the surface, the more the surface shrink. And therefore, you can see increase in the intensity of magnetic field enhances the cooling. It enhances the shrinking rate of the surface. You can see. This is extremely important. And these are got through the numerical simulations. And this is lower branch, this upper branch. It tells you that when you put magnetic field or nanofluid to cool a surface, the shrinking rate is enhanced. Now, these are the normal solution. Here we are talking of stressing now. For stressing, you can see here, my lambda here, we take lambda to be 0.1. Lambda is positive here. Lambda, for all this graph, lambda is positive. Positive lambda, which is stressing. Note that for positive lambda, only unique one solution occur, not two solutions. But you can see here, when you use alumina and copper, you can see copper is that here for this velocity profile. The red one is alumina water. You can see copper water will flow close to the surface. That you can see the body layer thickness, the momentum thickness of body layer for copper water is smaller. That is, this is the surface of the plate. This is free stream. Free stream is this surface of the plate. So copper water move closer to the surface compared to alumina water. So copper water move closer. Copper water, which is the dark black line, is a better coolant. It takes more heat because move close to the surface. The momentum thickness of copper water is smaller is thinner compared to the alumina. So copper water is a better better coolant. It moves close to the surface and takes more heat. And you can see here, the velocity also, you can see when you do sleep. Without sleep, this is what you are, the blue one. As you are increasing the lubrication of the surface, you are cooling. You can see the velocity increase. You can see due to the sleep, velocity increases on the surface. And the bad layer thickness is also reduced. Without sleep, the momentum thickness is high, which means the fluid does not move close to the surface. Large momentum thickness, momentum body layer, means the fluid is not touching the surface properly. But when the thickness is low, is small, that means fluid is getting close to the surface. So increase in X means increase in the slipperiness of the surface. Fluid is slippery, touching the surface, and therefore it's taking more heat. So those are the things you can confirm from here. And also here, this is for stressing surfaces. Magnetic field also, increase magnetic field reduces the momentum thickness, momentum body layer thickness. You can see here, we're talking of stressing. This one is shrinking, lambda negative, stressing lambda positive, 0 when it's no sleep. The surface is stationary. It's not shrinking or shrinking. I mean, 0 is when the surface is not shrinking or it's fixed, stationary surface. You can see here, as you increase in shrinking, you can see here is where you're having blue one represents shrinking. The thickness of body layer is very high. Because when surface shrink, it pushes the fluid away. It's shrinking, trying to push the fluid away from the surface. So when it's shrinking, it's pushing the fluid away. So therefore, the thickness of body layer is high. It's supposed to be high. It's bigger. The fluid may not touch the surface properly because when it's trying to push it away, and fluid is forcing itself on it. But for stressing, thickness is low. So the thickness of body layer decreases with increase in stressing, and the thickness of body layer increases with decrease in with increase in shrinking. Increase in shrinking enhances the body layer, the momentum body layer thickness. Increase in shrinking enhances the momentum body layer thickness. Increase in stressing decreases the momentum body layer thickness. Stressing allows you to touch the surface. And when it's 0, when the surface is fixed, then you have this one. So just take note, those are the results observed. And for temperature, it's also obvious because it's obvious. You can see here, as you increase S, which is stressing. As you increase the stressing, the sleep rest of the surface, the fluid is taking more heat from the surface. And the temperature of the surface, you can see temperature of the surface decreases. Temperature of the surface decreases because more heat is taken from the surface. That means the Nusselt number enhances. Heat transfer enhances, and you can see the temperature here decreases with increase in S. Also, Eckert number talks about internal heat generation. The internal heat generation in the fluid, as you increases it, the nanofluid also increases because internal heat generation in nanofluid. Those are due to what you call your thermophoresis, Brownian motion, and so on. All those things cause internal heat generation. Also, this causes dissipation of nanofluid, causes internal heat generation as it's flowing. Increased internal heat generation due to shear rate, due to the flow of the nanofluid. It enhances Eckert number. As Eckert number increases, the temperature of the nanofluid also increases. This temperature of nanofluid increases with increase in Eckert number. So here, because of the time, you can see increase in nanoparticle volume fraction. It increases also the temperature of the nanofluid. Because I've told you, nanoparticle, although if you look at the Borgiano model, you can see the effect of nanoparticle due to our thermophoresis and Brownian motion. It enhances the temperature. Because of that, although enhancing temperature also enhances the Nusselt number in the case of nanoparticle compared to the slippery of the surface. So you can see increase in nanoparticle enhances the temperature. And this one is obvious because when the fluid moves closer to the surface, it takes the heat more and the fluid becomes very hot. And you can see this one also for shrinking. You talk of shrinking for upper solution branch, the temperature decreases. If you increase the shrink, and for you can see here, for shrink, this is the temperature. For stress, the temperature decreases here. As we move from shrinking to stressing, minus 0.4, minus 0.2, 0.2, 0.4. You can see this one starting from minus. That means a shrinking surface, the nanofluid on a shrinking surface will be very, very hot. We have much higher temperature than on a stressing surface. Shrinking surface, the fluid will be of high temperature, and that is sensible because when the surface shrink, there's a more interaction between the fluid and the surface. The shear stress must be high. Because the surface is shrinking, pushing the fluid is forcing itself on it, more heat is generated. Therefore, we expect to have high temperature of the nanofluid. But for stressing, the surface is stressing the direction of the fluid. So the friction between the fluid and the surface is low. Therefore, the temperature of the fluid, of nanofluid, will be less. So these are the results. Magnetic field also enhances due to jaw heating. Jaw heating makes magnetic field to enhance. So these are the results which we have. Let's go to conclusion. For conclusion, nanofluid velocity increases from the wall towards the free stream. Velocity banding layer thickness, you have it like that. These are the conclusion. And you can see this one, aluminum water nanofluid is greater. That's one of common. Velocity banding layer thickness decreases with an increase. With an increase in the value of this parameter, nanofluid temperature decreases from the wall towards the free stream. All these I've mentioned already. Finally, to enhance the cooling rate at heated surface using nanofluid, it is advisable to regulate the value of various embedded parameters with respect to engineering and industrial application. So these are the references and so on. Thank you very much. I know I've moved, you give me from 2 to 1:30, I mean to 2:30. So I try to move above that, but it's okay. Thank you very much for inviting me. Let's go to question time. You can give me any question you think you want me to answer. Thank you very much. This is question time. You can ask questions. Thank you very much.
Thank you, Professor.
Yes.
I request Arnab, Dr. Arnab, Assistant Professor, Department of Mathematics, GSS, to read the questions. Over to Arnab.
Professor, please stop sharing your screen.
Yeah.
Hello, Professor McIntyre.
Questions.
Please stop sharing your screen.
Question. Hello, can you hear me?
Yeah, sir. Sir, please stop sharing, sir.
Okay. Oh, stop share. Okay.
Yeah.
Yes.
Okay. Okay.
Thank you, Professor McIntyre, for your outstanding talk. We have learned so many important things regarding the stagnation point flow. By your talk, many of the participants will surely be inspired to do research in mathematics, especially in the fluid dynamics. Professor, with your kind permission, I am sharing few doubts posted by the participants. Please clarify their doubts.
Please, can you tell them to mute their speaker? I mean, their mic, so that I can talk. They are speaking. I'm hearing what they are saying. So,
Actually, Professor, they have asked a question in the question answer section in this Zoom meeting.
Okay. Now, can I answer the questions?
Okay, the first question is from Professor Pradeep Kumar. The question is, in stagnation point flow over shrinking permeable sheet in the presence of the magnetic field, does dual solution exist for a certain range of shrinking length?
Okay. Now, the answer I said, in the stagnation point flow over shrinking permeable sheet in the existence of magnetic field, do dual solution exist for a certain range of shrinking length?
Yeah.
Listen carefully. For shrinking permeable sheet, yes, it is true, there is dual solution. Dual solution exists for shrinking permeable. If the sheet is permeable, as long as it's shrinking, dual solution exists. As long as the sheet is shrinking, dual solution exists. That is answer to that question. There is existence of, yes. Now, can we use hybrid nanofluid for better? Yes, thank you very much. Hybrid nanofluid can be used. Hybrid nanofluid, you can mix. For instance, you know that copper is not a stable material. Aluminium is not a stable material, but aluminum oxide is a stable material. Copper oxide is a stable material. Copper has a very high thermal conductivity compared to copper oxide. Aluminum has high thermal conductivity compared to aluminum oxide. Therefore, you can mix a percentage of a stable nanoparticle like aluminum oxide with another oxide with a metallic like copper to get a very better result as hybrid nanofluid. You can take copper, maybe 5% of copper mixed with 5% of copper oxide. Because if you copper with aluminum oxide, because if you use copper only, copper will get oxidized. When you put copper, it gets oxidized, it becomes copper oxide. So hybrid nanofluid is the best way to go. Is the best way to go to get a better result. Hybrid nanofluid. That is, take two nanoparticles, one stable, the other one unstable. Mix them together, not more than 10%. You get a better result than using only copper. Because copper will not give you results better, because copper will get oxidized. Put copper in water, it becomes copper oxide. After some time, you get oxidized. Use iron. Ferrous will become ferrous oxide. They get oxidized quickly. So their property changes. quickly. But the property of aluminum oxide does not change. It's a stable property. So hybrid is good. Now, this is another question. What is the difference
Another
between
question is from
symmetric?
Dr. C.S.K. Raju.
Yes.
Yes, what is the difference between symmetric and axisymmetric flow? He has asked.
Axisymmetric flow. Okay. Listen carefully. Listen carefully. Symmetric flow is a flow over a body which is not cylindrical. It means, for instance, if you see what I showed you before in stagnation flow, the stagnation point, it divides both left and right of the fluid. It hits the thing, then fluid started flowing, spreading left and right. That line
Thank you, Professor McIntyre, for clarifying the doubts.
is a line of symmetry. It's a line of symmetry. The line of divided is a line of symmetry. Symmetric flow of the same thing. Answers may talk of the same thing, but we use axis symmetry more when you talk of cylindrical body. Flow in a cylinder is axis symmetry, because in cylinder you don't have the left and right is cylindrical. Therefore, the flow is inside. So the axis of the cylinder is called axis symmetry. So flow, if you cut cylinder into two, the upper and lower of it is the flow is symmetrical along the axis. We call it axis symmetry. Symmetry along the axis of the cylinder. That's called axis symmetry. But symmetry is general, that is divided into two. So just take a look. Use the word aspect more in cylindrical coordinates in a symmetrical body than when you have geometry, than when you have other geometry. Symmetry can also be used. Now, question: if any conducting fluid flows through a rotating channel, yes, the flow has primary and secondary velocity, yes. If nanofluid flow through the same rotating channel, how is the velocity of the fluid? Is that velocity also has? Yes. If you have a rotating channel, the concept of primary and secondary flow is associated with the fact that the channel is rotating. Whichever fluid you use, whether your fluid is nano or no nano, there will be secondary and primary velocity. Because the fact is, because the channel is rotating, there will be secondary and primary velocity. And that comes from the model. The model equation will involve the secondary and primary in terms of the velocity because of rotation. Now, when you have nanofluid, you are going to have secondary and primary velocity. It's automatic. That's not because of nano, but the secondary and primary velocity, their magnitude will be different. The magnitude of primary and secondary velocity will be different in nanofluid compared to ordinary conventional fluid. But you will always have secondary and primary. There will be reverse flow because of the rotation. Fluid will be there will be reverse flow. Negative velocity will be there, like positive velocity for primary. Secondary, you have reverse flow. You have all these things taking place. There will be always secondary and primary velocity for nanofluid when the channel is rotating. And that is because of the geometry of the problem, not because of nanofluid. The nanofluid will only give you different magnitude. That's what will happen. Just take note of that. So, any question, any further question? Any question? Can you post the question online so that you can see?
Vishnu. Vishnu.
Sir.
Any question? Although I see, okay, thank you. There's a question here. by seeing the particular form of KNF over KF, how can we understand which kind of nanofluid model it is? Okay, listen carefully. Nanofluid model, listen carefully. There are two types of modeling nanofluid. There is what we call single phase model. Single phase model. And that single phase model assume that the temperature and the fluid, they are homogeneous. They move together. Therefore, you only need the continuity equation, the the momentum equation, the energy equation. Those are the three you need for single phase model. In that case, you have KNF over KF, because you are now dealing with the thermal conductivity of nanofluid and that of base fluid. You use that when you are using single phase model. And your nanoparticle now will be a constant. Will be a constant. Your nanoparticle phi will be a constant in terms of phi, which is percentage you use. The other second model is called Boggiano model. The Boggiano model for nanofluid. In that case, you assume that your fluid and the nanoparticle are separate. They are different. They are not moving homogeneously. Therefore, you want to know the distribution of nanoparticles in the base. We call it two-phase model. Two-phase. One phase for the fluid, one phase for the nanoparticle. In that case, you need 4 equations. You need 4 equations. The equation you needed, you need to add concentration of nanoparticle equation to it. Equation represents the concentration of nanoparticles. In that case, you don't need to have KNF and KF. It's not there. In that case, you are now looking at the effect of nanoparticle itself. You want to look at distribution. In that, you don't use phi. Your phi you will use comes from your concentration equation or dimensionless concentration equation. That's where your phi comes from. You don't use phi to be 0.1, 0.2, and 0.01. It's not involved in the two-phase model. Your concentration equation is that the equation of nanoparticle. You now see the spread of nanoparticle in your base fluid. You assume the base fluid is moving, the nanoparticle is moving. Base fluid and temperature, they are uniform, then the nanoparticle is different. Then you want to see how nanoparticle distributed within the base fluid. So that's where you have concentration equation. There are a lot of mistakes in journals, in papers, where people mix single phase and two phase without appropriate logistic the logic of the mathematics involved. Yes, 2 of them can be mixed, but there is a way of doing it, of modeling it. In fact, there is a paper I published recently, and I can say it's the first paper in combining the two. If you check the journal of calometry, journal, it's called thermal calometry or something this year. Calometric and calometric and so on. It's probably this year. That introduced how to merge the two together, both single phase and the single phase and two phase, where we are able to try to manage them together. But under normal circumstances, single phase for two phase, you don't need KNF and all those things. You don't be talking of copper. All you are looking for in two phase is the effect of thermophoresis and Brownian motion that comes from your nanoparticle in the equation of nanoparticle. Thermophoresis from the temperature that is generated through to the interaction of the nanoparticles and the Brownian spread of nanoparticles. So you have momentum equation, energy equation, concentration equation, and the conservation of mass equation, which is a continuity equation. Those 4 equations you will use. Without talking of copper, you can assume generally your material is a nanoparticle. So you don't put copper, but you can also use, the only way to represent your actual nanofluid is from your Prandtl number. Prandtl number will tell you, use Prandtl number of 6.2 or 6.7. You say it's a water-based nanoparticle, nanofluid. But the particle for two-phase model can be anything. But when you merge them together in a logical way, without violating the mathematical logics that is involved, then you can be talking of copper and so on and so forth. But not to just put them together. So that's all I can say about that.
Thank you, Professor Makinde, for this fruitful discussion. Over to Shashikala Madam.
Thank you, Professor, for an excellent presentation on modeling stagnation point flows of MHD nanofluid and its engineering cooling applications. We are very happy, sir, to have you here. And your presentation is very informative to the participants.
Thank you very much. Thank you very much. Thank you very much. So I thank all the participants and I thank all the audience across the globe. Thank you for giving me the opportunity to share.
Thank you.
I also hear from you, and we can collaborate. If you want collaborations, you can contact me. My address, you know my email address. Contact me. I'll be able to assist you in one way or the other. If you show me what you want me to help you, I'll be able to assist you. We can collaborate across the globe. That's how knowledge is shared. Knowledge is shared globally. Let us share knowledge. And if you have any area of assistance, contact me. Even in the area of biomathematics, if you are doing modeling of epidemiology problem, disease problem, anything, biological modeling, contact me. I've got a lot of work I've done in that area as well. And I have a lot of collaborators as well. I can assist you in the area of biomathematics, epidemiological, ecological modeling, issue of COVID-19, any disease. You can use that. Also for fluid, dynamical system, for fluid boundary layer, channel flow, anything fluid mechanics. You contact me, you can collaborate and do a lot of fantastic work together. Thank you very much. God bless you. Thank you.
Thank you very much, sir.
Yes.
Coming to the tomorrow session, Professor Ayman Badawi is delivering the talk on the zero divisor graph of the semi-group with zero. Tomorrow session will start at 6 p.m. onwards. I request everyone to join before 10 minutes to the session. And tomorrow is the last date. Yeah. Tomorrow is the last day. That is compulsory to attend the session. I request everyone, please fill the feedback form given in the chat box. Feedback form will valid only half an hour.
Hello, Professor Makinde.
Yes, yes. How are you? So how are you?
Hi, Professor.
Yes. How are you? It's nice meeting you. How
Thank
are
you, sir. Thank you.
Thank you. Thank you. Okay, I've seen your name, and thank you very much. God bless you. Thank you. Yes.
Bye.
Yeah.
Bye.
Yeah. Okay, how are you? Thank you. Thank you.
Thank you.
Dr. Venkat Swelu, thank you.
Thank you so much, sir.
Yes, thank you. God bless you. Thank you. And
Thank you so much,
Dr. Duga Prasad. And there are so many people I know here, so many people. I've seen their name. I've worked with them, and God bless you. Thank you very much. I've seen so many people names here that I know very well. Thank you very much.
Thank you so much, sir, for your wishes.
Thank you. God bless you. Thank you.
Thank you so much.
Okay, look forward to meet you one of these days. Anytime I visit India, I will come around.
Please, sir, please visit to my university, sir, once.
But maybe next year when everything is settled, if everything is peaceful, anytime I visit, I will visit most of the places as well. Thank you very much.
Always welcome, sir. When you come to India, please visit my university, sir, once.
Yes, I will. I will let you know anytime I'm coming. I will
Yeah.
let you know. Thank you. Thank you very much. Thank you.
Thank you, sir.
Okay, thank you. God bless. Thank you. Yes.
Thank you, all the participants. Tomorrow is the last session at 6 to 7.
So go to that. Go back to
Sir, slide.
stop recording. Stop recording. Live session also stop.
YouTube live also. Can stop it live.
First stop schedule.
There is the team.
First mute. First stop recording.